Welcome to a session on acceptance angle and numerical aperture. First, let us see the definition of acceptance angle. Acceptance angle may be defined as the maximum angle of incidence to the axis of optical fiber at which the light ray may enter the fiber so that it can propagate through total internal reflection. Here you can see this angle alpha I is the maximum angle made by the light ray with an axis so that it is propagating from one end to the another end by the process of total internal reflection. In this case, this particular angle of incidence alpha I is called as acceptance angle. The light ray is launched from one medium of refractive index N0 into the other medium of refractive index N1. Here you see the light ray is launched from air medium whose refractive index is N0. So this light ray is launched into this medium whose refractive index is N1. Of course, N1 is the core medium and N0 which is having the air medium. Refractive index N0 is the air medium. Refractive index N1 represents the core. The ray enters the fiber from a air medium at an angle of incidence of alpha I at the point A. The angle of refraction at A is alpha R. Here you can see. So the angle between axis and the incident light ray is alpha I. So this particular light ray entering this particular core medium at point A. Now it is getting refracted because the angle of incidence is less, so that it get refracted. So this refracted light ray having an angle of refraction of alpha R. This ray undergoes total internal reflection at B at an angle theta. The minimum angle for total internal reflection is theta equal to theta c, which is critical angle. So which means that this refracted light ray goes to the core cladding interface. So what it means is here core ends and cladding starts. This particular region is called as core cladding interface. So at core cladding interface, if this angle of incidence theta is greater than critical angle, then this light ray undergo total internal reflection. From triangle ABC, alpha r is equal to 90 minus theta. So here you can see the triangle ABC. From this, what we can write the math is alpha r plus theta equal to 90 degrees. Alpha r plus this theta equal to 90 degrees. From that, what we can write is alpha r equal to 90 minus theta. If we apply Snell's law for this particular condition, so light ray enters from rarer medium to denser medium, which means air medium to core medium. So if you write the Snell's law, we can write like this: n0 sin alpha I equal to n1 sin alpha r. So here n0 is the refractive index of the first medium, air medium, and n1 is the refractive index of the second medium, core medium. So these are very clear. And this is the angle of incidence and this is the angle of refraction. Here angle of incidence is alpha I in a rarer medium, alpha r is the angle of refraction in a denser medium. So from the Snell's law, finally we can write like this: n0 sin alpha I equal to n1 sin alpha r. From this we can write sin alpha I equal to n1 by n0 into sin alpha r. So we can write sin alpha r as 90 minus theta. So n1 by n0 into sin alpha r as 90 minus theta. At 90, sin becomes cos. So n1 cos theta by n0. If theta is less than critical angle, if this theta is less than critical angle, what happens? The ray will be lost by refraction, which means that if this angle of incidence, this theta, angle of incidence theta is less than this critical angle, then this light ray enters into the cladding medium rather than undergoing a total internal reflection like this. It will go like this dotted line. Here this light ray is making an angle of incidence at the core cladding interface theta less than critical angle. So it enters cladding medium. So the limiting condition is at least theta equal to theta. See, angle of incidence at a core cladding interface equals to critical angle. Now, at that particular situation, incident angle alpha I is called as maximum angle alpha I max. Let us substituting this limiting condition in equation 1. So sine alpha I, instead of alpha I, we can write alpha I max. So sine alpha I max equal to n1 cos theta. At this particular condition, theta equal to theta c, n1 cos theta c by n naught. But we know cos theta can be written as 1 minus sine square theta. 1 minus sine theta, we can get it as n2 by n1. So 1 minus n2 by n1 whole square. So the above equation becomes sine alpha I max. Sine alpha I max equal to n1 by n0 into. So just now we can write the cos theta c as 1 minus n2 square by n1 square. So by simplifying that, we can write square root of n1 square minus n2 square by n0. So this is the equation. Acceptance angle sine alpha I max can be written as sine inverse of n1 square minus n2 square by n0. So this is the expression for acceptance angle. The maximum angle is called as acceptance angle or acceptance cone half angle. So here this alpha I max is called as acceptance angle. Light launched at the fiber end within this acceptance cone alone will be accepted and propagated to other end of the fiber by total internal reflection. Here you see, this is the alpha I max. If you rotate this alpha I max by taking axis as the reference, so we will get a cone shape. So this is called as acceptance cone. What is the specialty of acceptance cone is the light ray launched within this acceptance cone can easily propagate from first end to second end by the process of total internal reflection. If a light ray is launched beyond this acceptance cone, it simply escapes. Here you can see, because it doesn't satisfy the total internal reflection condition. Let us see the concept of numerical aperture. Light gathering ability of the optical fiber is called as numerical aperture. So numerical aperture mathematically defined as a sign of maximum acceptance angle. So numerical aperture NA equal to sign of maximum acceptance angle alpha I max, that equal to square root of n1 square minus n2 square by n0. This is the expression for numerical aperture. So numerical aperture equal to square root of n1 square minus n2 square by n0. We can write it as, actually it is in the form of a square minus b square. So we can write a square minus b square as a minus b into a plus b. So n1 minus n2 into n1 plus n2, and we can write n0 equal to 1 because n0, we launched the light ray from air medium to core medium. So we can take n0 as 1. By taking all these considerations, Na equal to n1 minus n2 into n1 plus n2. Define fractional difference in refractive index delta as n1 minus n2 by n1. Here I am assuming that n1 minus n2 by n1 as delta, which is also called as a fractional difference in refractive index. So from this we can write n1 minus n2 as delta into n1. Substituting this value n1 minus n2, we can write as delta n1 as like this. Numerical aperture equal to square root of n1 minus n2. So here you can write delta n1 into n1 plus n2 into n1 plus n2. So for most of the fibers, n1 is approximately equal to n2. So we can write n1 as n2. So the above equation becomes delta n1, n1 plus n1, 2n1, because n2 can be written as n1. So n1 into n1, n1 square. If you take out from square root, it becomes n1 into delta 2. So root 2 delta. So numerical aperture equal to Na equal to n1 into root 2 delta. This is the another expression for numerical aperture. Generally, the value of numerical aperture ranging from zero point 0.1 to zero point 0.5. So zero point 0.1 means low numerical aperture, zero point 0.5 means high numerical aperture. So zero point 0.1 numerical aperture means that light gathering ability of that particular fiber is very low. Zero point 0.5 numerical aperture means the light gathering ability of that particular optical fiber is very high. Thanks for watching.